All right, let's take a look at set 1 of the 2023 AP Physics C, E, and M questions. Solutions aren't out, so these are my best guess as solutions. If I inevitably make mistakes, I will put them as a pinned comment in the description. So students perform an experiment to determine the value of the vacuum permittivity epsilon naught. Sphere 1 is non-conducting charge with plus Q attached, and a non-conducting sphere with positive Q. Sphere 2 is hung from negligible mass length L. Sphere 1 is brought near without touching. Sphere 2, as shown. Equilibrium is established when the centers of the two spheres have the same vertical position, are in a horizontal distance d apart, and the string is at an angle theta with the vertical. On the following dot that represents sphere 2 at the position shown in the figure, draw and label the forces acting on sphere 2. So sphere 2's got gravity. Okay, it's got a rope pulling on it. We got the tension force from that rope pulling it. And there's an electrostatic force. They're both positive and they're repelling each other because they're the same charge. So it's going to be directly to the right like that. And then we'll call that the Coulomb force. I usually use FC for that. You can use E if you want for electrostatic force. Derive the relationship between theta and show that D equals... All right, so how are we going to handle that? We're going to just break down our free body diagram here, right? So like if you look at this guy, and you shouldn't mess with that, but you know, like if you decompose the forces, it really should be T cosine theta to the left, to the up, and T sine theta to the left like that. And then I have mg, and then I have my electrostatic force or Coulomb force. And because the acceleration is 0, it's just suspended there, right? Then all the x forces are equal. So T sine theta is going to equal my Coulomb force, which is K Q times Q divided by the distance, and the distance is D. The distance between their center masses is D squared. And then vertically, you have T cosine theta equals mg. So then you just solve for T. It's mg over cosine theta, right? We're going to plug that into there. So we're going to have mg tan theta, sine over cosine. It's going to be sine theta divided by cosine theta is going to be kq little q over d squared. And you multiply by the d squared, move that down, you'll get d is equal to square root of k big Q little q over mg tan theta. Oh, they use k. I hate the 4 pi. I always use k. Okay, so k is equal to 1 over 4 pi epsilon naught. I don't know why they just... It's just more writing, so I'm lazy, okay? I'm honestly lazy, so whenever I have to write more stuff, right, I honestly, I don't write it like that. Okay, these values are collected one trial. Calculate the expected tension force by the string. Let's see, they have Q, they have theta, they have D. What could you solve for? I guess you could solve for mg if you wanted to, based on this data. Yeah, I would just say mg, which is T cosine theta. So mg over cosine theta. So let's solve for mg for this one, just to make it easier. So mg would be k big Q little q over d squared, right? So mg tan theta is going to be this times that. So if I do, you know, it's going to be kq big little q over d squared. That's mg over cosine theta. Oh, sorry, I got to divide by tan theta here. So over tan theta, all over cosine theta. I'm a little tired. This is I'm just burning through these FRQs. So, okay, so just plug in the numbers now. The charges are the same. The distance is 0.057 squared divided by tangent of 12 degrees. And then all of that divided by the cosine of 12 degrees. Oh, I am in radian mode. I should double check I'm in degree mode before I do all these calculations. Okay, so retype that in, divided by cosine of 12 degrees. I get the tension, which is mg over cosine theta, which is 0.002167 newtons. It's pretty... I guess this is a pretty light thing. Must be pretty light, yeah, if you're going to have it dispel by that much. Yeah. Students vary d and measure theta after equilibrium is reached. D squared versus 1 over tan theta. Draw the best fit line for the data. All right, so we're going to draw a line that's like... Oh, that's good. Okay, yours could probably be better than that. Okay, so They loved it on this year. They just wanted you to understand how to do linearization more than anything, okay? So this one, they gave you the equation. So d squared is just going to be with this thing without the square root. It's QQ. I'm just going to write as K. I am way too lazy to write 4 pi epsilon naught every time. You're just going to have to live with that. KQ little q over mg and make this 1 over tan theta. Right? So this is my y variable. This is my x variable. So this is my slope. So my slope is going to be K big Q little q over mg. Okay, so we want to calculate the slope of this guy. Let's pick a couple of points. I'm going to pick this point over here. That's like 11, 11.5. The y value is 0.008. This is 0.009. This is like 0.0085. What about, say, this point? This is about 3 and 0.002. Okay, so let's just do that. So this is going to be 9 times 10 to the 9. Or I'm just plug in the numbers. So I'm going to get 0.0085, and then there's no special things about the units. Minus 0.002 divided by 11.5 minus 3. Right? So you're going to get that number as your slope, and then you're going to solve. Oh, this is why they wanted the permittivity. That's why they're making you write all this. Okay, fine. 1 over 4 pi epsilon naught. Okay, happy? So we're going to take this number calculation divided by 11.5 minus 3. It's entirely possible I entered stuff into the calculator wrong, so you're just going to have to live with that part. So divided by q multiply by m. G, I'll use 9.8 because I'm out here anyway. So then I need to multiply by 4 and pi. And then that's 1 over epsilon naught. So I get epsilon naught. It's about 7.65 times 10 to the negative 12. Okay, it should be 8.85. Close enough, I guess. Maybe this data, I don't know. Maybe I should have made it a little steeper, probably. I don't know. Okay, students modify the experiment by replacing sphere 1 with conducting sphere 3 that is same size and charge plus q. The experiment is repeated. The circle in the represents sphere 3, then spheres 2 are at equilibrium. On the circle, draw a positive charge to represent the location of the highest concentration of the excess positive charges, a single plus sign. Okay, so what are they doing? They're replacing sphere 1 with the sphere 3, and it's a conducting one now. So we want to know like where the positive charge is going to be. Well, what's going to happen is this is positive. They're going to the positive charge is going to kind of like repel each other and be over here because this is a positive charge, and the negative charges will be attracted toward there. So it'll be like a positive will be further away. So we'll put it like right over here. Briefly explain your reason for the sketch. They just want to single that. Yeah, because the electrons will be drawn to the right. Due to the positive Q on the other sphere, leaving more positive charges on the left. Something like that. In the original experiment, when the centers of the two spheres are horizontal distance d1 apart, the string makes an angle theta 1 from the vertical. In the modified experiment, when the centers of the two spheres are horizontal distance d1 apart, string makes an angle theta 2. Is theta 2 greater than or less than? It's actually going to be less than, because now that the charge is separated further, you're going to have a weaker electrostatic force, because you're going to have more like attracted to here. It's just going to like weaken the overall. Wait, is that true? Let me think about this. Okay, so sphere 2 has a non-conducting charge here, so the charges are fixed in the same spot. But in this one now you have a positive and you have a negative here. So this is going to, so the positive charge is going to be further away. It's going to weaken that repulsion force, and this negative charge is going to be drawn to here. So that's going to actually add in a little bit of net force towards it. So the end result is the electrostatic force is going to be weaker with this conducting sphere, and so that's why the theta is going to be smaller. So the minus charges are closer, and positive charges are further away. And that results in a weaker electrostatic force. Repelling force. It's not going to draw towards each other because the net charge is still positive, but it's going to be a weaker repelling force. Okay, that's all I would say. All right, let's look at the second one here. Two horizontal parallel conducting rails are separated by distance L equals 0. Resistor resistance R equals 30.3. Sorry, connects the rails. A horizontal ideal spring is located between the rails. Right end of the spring is free to move, and the left end is fixed in place. A conducting bar of mass 0.23 kilogram placed on the rails is in contact with the spring, which is initially compressed. Frictional force and resistance of the bar and the rails are negligible. At time t equals 0, the bar is released from rest and pushed to the right by the spring. At t1, the bar loses contact with the spring and slides to the right. T2, the bar enters and travels through a uniform magnetic field of B equals blah, directed towards the beige as shown. T3, the bar enters a region where the magnitude of the uniform magnetic field is still 0.5 but directed out of the page. At time t equals 4, the bar enters a region with no magnetic field. Okay, consider the time between 2 and 3. So this is T2 is when we're in this region here, and T3 is when we're in this. So this region here is T3. This region here is T2. Okay, fine. Between T2 and T3. So, or actually, we'll just say, actually, let me put the times like this. So the whole region, we should say. This is T2 occurs, and then right here is when T3 occurs. So between T2 and T3 is when we're in this region. Following diagram of the bar, draw an arrow indicating the direction of the net force exerted on the bar at time TB. If the net force is 0, write F net is 0. Okay, so basically, if it's moving to the right, you're going to get a repelling force that's going to go to the left here. You can reason that out if you want. Or you could just draw a single arrow. You just need to draw a single arrow. Why is that? Because it's not going to accelerate. It's not going to help it move. It's going to induce a magnetic field that's going to oppose. So, like, oh, actually, it's after we entered. My bad. Sorry. I don't know what I'm thinking. So, after we've entered the magnetic field region. Oh, so this is a conducting bar. Oh, no, so I have it right. So what's happening is the area is changing, right? Because this is the area of the loop. And as it moves to the right, the area is changing. So the area changing is going to cause an increase in the flux into the page. So you're going to induce a magnetic field out of the page. If you have a magnetic field out of the page, that means the induced current has to be like this way by the right-hand rule. Like my thumb is up, and then the fingers are pointing out of the page. So it'd be like this. And then if you think about the force, you do the QV cross B. So your charge is going up. Magnetic field's into the page, your thumb's pointing to the left. So it's going to be the net force to the left there. At time TB, the speed of the bar is that. Calculate the magnitude of the current at times TB. Okay, so the magnitude of the current, we always do as V over R, and we always do V as the induced, the change in the flux, the derivative as a function of time. And the derivative of that is B times A. But the magnetic field is not changing, so it's just dA dt. How is the area changing as a function of time? It's length times width. The L isn't changing, so it's just, B times L times dW dt, and that's the velocity. And so all I did was derive that equation, the BLV for you. So the magnetic field is, let's see, what is the magnetic field? What did they tell you? 0.2, it's 0.5. Okay, 0.5. The L was, I don't know, like L is 0.4, and the velocity is 2.5. So that is 0.5 volts, and so the current is going to 0.5 divided by the resistance. The resistance is 0.3 ohms. And that is 1.67 amps. Calculate the magnitude of the net force exerted on the time at TB. Oh, okay. F net, you would use just ILB. You don't need the sine theta because it's already perpendicular. So it's 1.67 times 0. What did I say L was? L was 0.4. And the magnetic field is 0.5. So this is the force from this wire, which has a length L. This part of the current is where the force is. These ones that are parallel here, they'll exert forces, but they'll kind of be like cancel each other out. So just be this guy here. 0.33 newtons. On the following axis, sketch the graph of the speed as a function of time between 0 and t4. So if you think about what's happening, okay, if you think about the force is changing because your as a function of time, like your voltage is BLV, right? And your current, or your if you look at your net force is going to be, let me just see if you've never seen this before, it's ILB. B is times BLV, so it's V over R times LB. Okay, so that's BLV over R times LB, so those are squared. So that is B squared, L squared, V over R, and that's going to equal M dV dt. Now this is a negative sign because this force is opposite the direction of the velocity. Okay, so if you look at this is an exponential. So the first if you do separation of variable, get exponential. Anyway, it's going to start. Okay, so 0. So the first part is the spring. The first time it's gaining kinetic energy. So as a function of time, you know, you think about you always want to think about the acceleration. It's really like kx. So the net force is kx, which is ma. So the slope is steepest here because the spring is the most stretched at that point. And so then it's like, I don't know, then it's like that. And then it's like a constant velocity because the spring has let go. Okay. And then from here, we have this force. Now, this is going to exponentially approach 0. So that's what kind of happens here. Okay, because we enter in a force, and basically the bigger the velocity, the bigger the change is going to be. So it's going to do this. And then right here enters the end again. It's going to do the exact same thing. So actually the force doesn't change. The current's going to switch directions, but the force is still going to do this. So it's going to decay to 0. So there's no like kink or anything like that. It's just going to continue. Because even though you change the direction of this, the current is going to switch immediately to be the other way so that the force is still to the left. So then it's still going to just make it slow down and slow down and slow down. And it's this differential equation is exponential. It'll approach 0 if you do the separation of variables to reason that out. The scenario is repeated with an additional resistor. Resistance R as 0.3 is connected shown. Determine the total resistance of the closed circuit for the new scenario. Okay, they added 2 resistors. Well, those are 2 resistors in parallel. So, right, because they're just connect on the top and bottom. So it's, you do 1 over R equivalent is 1 over 0.3 plus 1 over 0.3, you're going to get the R equivalent is going to be 0.15, half the resistance, because they're the same. In the original scenario, the magnitude of the acceleration of the bar immediately after the bar enters the uniform is A original. In the new scenario, the magnitude of the acceleration is immediately after the system is A new. Is A new greater than, less than, or equal to A original? Well, let's kind of look at the net force here. We said it was B, like if we look this out, the net force that we derived here was BL squared V over R. Okay, so B doesn't change, L doesn't change. The initial velocity doesn't change because you've launched it. When you increase R, the A is going to go down. Okay, so it's going to be less than. And you could either point to this derivation. You could also maybe make an argument about like, well, the force is ILB, so the current is greater, so the net force is... I don't know why I said less than. My brain's not working. It's greater than, right? Because R goes down, right? So then the net force goes up. R goes down, net force goes up, so the A goes greater than. I think I was reversing in my mind which one I was talking about. So the resistance is going to go down. That's going to increase the current. So you could talk about it from this point of view. The current increases, so the net force is going to increase, right? So some kind of argument like that. Describe a modification to MB or L that result in a smaller induced potential difference across the original resistor immediately after the bar enters the first magnetic field. Justify your answer. Modification to the mass potential difference across immediately after the bar first enters the uniform magnetic field. Smaller potential difference. Okay, where would our potential difference come from? Came from BLV, right? So the potential difference was B times L times V. So you could reduce L, you could reduce B, you could increase m to reduce the velocity. Any of those would work, right? Describe a modification. So you could decrease L. I don't know. Any of those. Decrease L. You could decrease B. If you change M, like if you increase M, then it's not going to go as fast. So you could increase M is another option. That would result in a smaller V. Because then the spring, when it pushes, is not going to push it as fast. Smaller V would, again, change the potential difference to be smaller. All right, third question. Last question here. Circuit shown consists of battery of EMF epsilon, resistors 1 and 2, each resistance R, and let's see, each resistance R, and capacitors 1 with C and 2C respectively. The switch is initially open, both capacitors are uncharged. At time t equals 0, the switch is closed. Write but do not solve a differential equation that be used to determine the charge Q on the positive plate of capacitor 1 as a function of time. Express your answers in terms of this. Okay. So, which one are we doing? We are closed in position A. So we're going to close this right here. And we're going to solve this differential equation. All right, so differential equation you always want to do is just sort of like Kirchhoff's Loop's law and stuff like that. And you want the charge on the capacitor. So first I would combine these two into a single resistor and just make it R over 2, right? Because two parallel resistors R will have an equivalent resistance of R. So then that's kind of makes it a little bit easier. So then when you do our loop rule here, the voltage drop across here is going to be, and the voltage drop across here have to add up, right? So you would say the voltage across the resistor plus the voltage across the capacitor is going to equal epsilon, right? So this voltage across the resistor is I times this R over 2. So this is I times R over 2. And then the voltage across the capacitor, we know Q is equal to CV. So that is equal to Q over C is equal to epsilon. Now, here's the thing. The I, the charge that's going into here, going into this positive side, I is going to be equal to the rate of change of the charge. So then you would say dq dt times R over 2 plus Q over C is equal to epsilon. That's a differential equation that involves functions of Q. R and C and epsilon are constants. Okay, sketch the graphs of the charge density on the positive plate and the total power dissipated by resistors as a function of time until steady state conditions are nearly reached. Okay, so the charge is going to be 0. I don't know why I would say charge density, just say the amount of charge, right? It's just divided. It's just this divided by the area. It's going to approach a level value. Did they want you to label the axis? No, they didn't say that. The power dissipated is... so the power you can think of as I squared R. The I is going to be initially very big, and then it's going to like decay to 0, right? Or you could think of it as the voltage is 0 and it goes up. So you could think of it as V squared over R. But either way, you're going to start off at 0. It's going to be a lot, but then so wait, they want the power dissipated by the resistor. Sorry. We'll use I squared R because that would probably be the easiest one. So what's going to happen is the current is going to do this. The current, right, it's going to spike up and then it's going to decay to 0. That's what happens with the current. So then you just do, and then because the current is like in series with the resistors, you just do I squared R. So it's going to have like it's going to spike up and then decay to 0 like that. Where that is like the initial current that's going through it as soon as you close the switch. At time t equals 1, the switch is closed to position B. Immediately after T1, the direction of the current is switched. Is the direction of the current in the switch directed toward the left, directed toward the right, or is there no current? So now we have charged the capacitor some amount. Okay, so now we've closed the switch here. Now, at this point, what's happening is there's a voltage difference here. This voltage difference is 0. So there's a higher potential. It's like a battery. So the current is going to flow this way from this capacitor to charge that capacitor there. Okay, because there's a potential difference between here. So the charge is going to flow that way. So it's going to be to the right. To the right. Charge will flow from capacitor 1 to capacitor 2. Higher to lower voltage, if you will. Determine expression for the... I don't know what if they want to justify your answer because... You could say because capacitor 2 has no charge. Has less potential. And no charge. Charge clearly can't, like, it has no charge. How could it possibly go to the left, right? Determine expression for the total charge in the positive plate capacitor 2 a long time. So a long time later, you wait a long time. What happens? There's no current. So you wait a long time here. Now this is 0 volts. This is, and they both have the same voltage, right? So like they have the same voltage here. Why? Because the loops, like they have to add, right? Like if I add to 0, so the voltage drop here. If there's no drop here, then this drop and this drop are the same. So they'll have the same voltage eventually. So you know that eventually VC2 equals VC1, which means Q2 over C2, right? Q equals CV equals Q1 over C1. But C2 is 2C and this is C, so this would be Q2 over 2C equals Q1 over C. And you know that we started off with Q0 charge. The total amount of charge has to be the same. Okay, so these C's cancel. And so you can plug, like, what do we want to find? We want to find Q2. So replace Q1. Q1, you're going to replace with 1/2 Q2 from this equation here. So you have Q0 is equal to 1/2 Q1 plus Q2, sorry, Q2 plus Q2 is 3/2 Q2. So therefore, Q2 is going to equal 2/3 Q0. Okay. Derive an expression for the total energy dissipated by resistors 1 and 2 immediately after time 1 until new steady conditions have been reached. Express your answers. Well, it's just the difference in the energy. So you could think about the energy. Where is the energy coming from? It's the capacitors. So initially, how much energy did we have? We have 1/2 CV squared. But we know Q0, so you know Q is equal to CV, so V is equal to Q over C. So this is 1/2 C times Q over C squared, which is 1/2 Q squared over C. So over C squared and C, one of those C's will cancel. So initially, this is how much energy we have. How much energy do we end up with is, well, we have 1/2 CV, each. Just look at the same, Q over C, Q squared. It's a Q1 squared over C plus 1/2 Q2 squared over 2C, because Q2 has a second. So it's like, this is the energy in capacitor 1, the energy in capacitor 2. And whatever difference in energy is how much energy we must have lost, right? So that would be easier. You could do an integration. You could set up the differential equation, do the currents, do the integral. That would be pretty painful, to be honest. So it's easier to just talk about the energy in the capacitor. So we know that Q1 has to be 1/3 Q0 because the total charge has to add to Q0. So this is going to be 1/3 Q0 squared over C plus 1/2 times, what is this? 2/3 Q0 squared over C. And that's going to be 1/9 times 1/2 is 1/18 Q0 squared over C. This would be 4/9 or 4/18 Q0 squared over C. So that's going to be 5/18 Q0 squared over C. So the change in the energy is going to be this minus that. This is 9/18 minus 8/18. That is 4/18 Q0 squared over C. Or 2/9 if you want. Okay, well, with the switch closed in position B, the parallel plates of capacitor 2 are moved, so the separation distance increases by a factor of 2. Okay. Okay. Determine the ratio of U2 to U1 of the energy stored in capacitor 2 to the energy stored in capacitor 1 as long as time after the plates of capacitor 2 have been moved. Justify your answer. So we're going to separate them. And the charge may not be the same, but we do know what's going to have to be the same when we do that is the voltage across them still has to be the same. If you wait a long time, there's going to be no current flowing. So we do know the voltage is going to be the same. Not that the charge is going to be the same, but that it's going to be 1/2 C1 V1 squared and then 1/2 C2 V2 squared. So this is 1/2 C V squared. This is 1/2 2C V2 squared. So now what we're going to do is, and this is so this is U1, this is U2. Now what we're going to do is if you double the distance, so capacitance, right, is kappa epsilon naught epsilon over the D. If I double the distance, that means the capacitance is going to be times 1/2. So now what's going to happen is this 2C is going to go to 1C, right, because it's going to be half. So the U2 is just going to be 1/2 C V2 squared, but it's the same voltage here. So they'll have the same. So U2 over U1 will equal 1. Because they'll have the same voltage, and now they'll have the same capacitance. You would say it's the same potential difference. And now it's the same capacitance, same C. With the capacitor still charged at part D, the switch is now closed into position A. Express your answers in terms of RC, Q naught fundamental. Derive an expression for the current of the battery immediately after the switch is closed to position A. So remember what happens here. Okay, so hang on a second. The capacitor is still charged as in part D. This part here, okay? So this part means that we're now at like C. This is getting like kind of confusing, to be honest. So we know that this is now C and this is C. And now we put it back into A. And it has to have the same charge, 1/2 Q0 now, because that's what's going to happen. So we move it from B to A, and now we're here. Okay, I get it. What are we going to do now? Derive an expression for the current through the battery immediately after the switch is closed. Okay, so the voltage across here. Okay, that voltage across it is equal to Q over C. So it's like, it's basically, it's half the voltage when we started. So we charged it and then we split it. So now this voltage is like, initially right now, it's half of the voltage that it was originally. Because originally we put Q naught over here. Now we have half of Q naught. So the initial voltage is half. That means the voltage drop across these resistors is also half an epsilon naught. Half epsilon, right? Because like the total voltage drop would be epsilon through this loop. So what do we want? We know the voltage equation for the immediately after. So the I0 through the battery is going to equal to the current through the both resistors, right? Or a single R over 2 resistance. And that's going to be 1/2 epsilon V over R plus 1/2 epsilon over R. Because each resistor, right? Each resistor in here is going to receive the same current because they have the same potential difference across them. Okay, so there's 1/2 epsilon across this guy. I don't know if this is making sense, but or if I'm rambling at this point. So yeah, it's going to be kind of like, that's going to be the kind of the voltage setup right there. Okay, so then that's going to be 1/2 plus 1 is going to be just epsilon over R. Determine the current I infinity from the battery a long time after the switch is closed. Well, after a long time switch is closed, there's no current through the capacitor, so the I is going to be 0. Right? No current through C. Where else would the current go? That's it.